Hello, everyone. Welcome back to another exciting chemistry video lessons by Adrenaline, the Bazooka Prophet, CEO, Adrenaline Global Online Tutorial Platform, an educational platform that is into every sphere of educational services. Now, in this particular video, we're going to be entering quantum chemistry, and the aspect of the quantum chemistry we are to actually talk about is what we call the Hückel's molecular orbital theory. A lot of students have been having issues with this part. Many do not know how to create the secular matrices for the Hückel's molecular orbital theory. And in today's video, you will be able to understand the basics and the foundation, and you will be able to create a 4 by 4 secular Hückel's determinant. So sit tight, relax, and be sure to get the best teaching from us. Quickly, let us talk about the Hückel's molecular orbital theory. Now, from what I wrote here on the board is that the Hückel's molecular orbital theory is simply a method that is used to study, take note, that is used to study pi electrons. Take note of pi electrons, right? In conjugated, underline, in conjugated and aromatic compound, meaning Hückel's molecular orbital theory is used to study what? The pi electrons in conjugated and aromatic compound. Now, what are the examples of these compounds that are studied using Hückel's molecular orbital theories? Number one, we have ethene, we have butadiene, we can also have the popular organic compound benzene. There are so many examples that we can use to study the Hückel's molecular orbital theory. But we should understand from the word conjugated, what should come to your mind? They have an alternate double bond. Conjugated is for the linear, while the aromatic compound are cyclic compounds. So we're going to be going into details. But before then, we should understand some of the basics in which Hückel's molecular orbital theory operates. Number one is the Sigma framework. The Sigma framework. The Sigma framework in Hückel's molecular orbital theory is always ignored, meaning it is not considered. Why? The pi system, which we are actually interested in, is treated separately. Another point again is to note that each of the carbon atom in the double bond system consists of a p orbitals, and it is the p orbitals that form the framework of the pi bonds. I hope you following. I hope you following. So let's go deeper. We should also understand that it is your understanding of the number of carbon atom that will give you the number of the p orbitals that will now form the framework of the pi bonds. For some persons who want me to go deeper into it, we are offering an online marathon classes for advanced level chemistry students, you can always do well to contact me through the following numbers on your screen as displayed above. So let's quickly continue. Let's not waste time. Now, there are some things we should know or take note about. And what is that? We've talked about all this. Now we'll talk about how they operate. Right? Now, there are some certain things we should take note of. And one of which is what we call the alpha. This alpha you are seeing here on the board is called the column integral. This beta you are seeing here is called the resonance. The resonance what? Integral. While this 0 is for other entities, which we soon understand even as we continue in this particular video. Now, what does this alpha talks about? The alpha is always on each carbon atom, meaning if I'm having 2 carbon, as in the case of 18, I'll be having what now? I'll be having 2 p orbitals, meaning there will be alpha on each of the carbon. That's why you saw it here. The alpha on each carbon atom, meaning the energy, the alpha is simply the energy of a p orbital, meaning 1 carbon, 1 alpha. While the beta is always bonded between the carbon atom. Let that sink into your head. That the beta is always bonded between bonded carbon atoms. And this is simply the neighboring what now? The neighboring atom. It will move straight to 0. 0 is when it is not bonded. So I'm going to erase the board now so we can create room to do the 4x4 circular matrix, and I'll be giving you a shortcut for that so you can actually follow and understand. Now, stay tuned. I'll be right back. So right about now, we'll be talking about the 4x4 circular Hückel's determinant. And a very good example of that is the butadiene, which is C4H6. So we're going to be working straight on it with simpler methods. Now, before we start, there are some things we must take note of. Number 1 is the alpha minus E. This one is simply the diagonal. The diagonal. Why the beta, this one is simply the neighbor. Why 0, this one is simply the non-neighbor. So we're about to build the 4x4 matrix now. Right? Because the reason for this alpha minus E is because we want to determine the energy. That is just the essence of it. So for those of you who might be finding it difficult, you can do well to you can always do well to reach me to break it more further. But before that, let us start. So what do we do? By the 4x4 is like this. Please take note. This is how they build it. 4x4, this is how they build it. We come here, the first one we take. So we assume that x, right? We assume that x, right, is equal to alpha minus E, so as to make the table easier for us to understand. So we come here, we put there to be x, put there to be beta, that's 1 carbon, 2 carbon, then here is 0, 0, 4x4. You don't understood now? The same thing here, x here is beta, here is 0, 0. You see it now? That's the row and column. Column, 4 column, while that of the row is 4 rows. So how do we build this? We build it in the form of diagonal. Look at it. So diagonal, 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 diagonal. That's that to be. So you build it like slant form. Telling you the shortcut now. Slant form. Then the neighbor will not be following. Is that understood? So let's go. Yeah. We build there like this, x. Move here like this, x. We'll move it like this, x. That's diagonal form, right? Then the neighbor here will be a neighbor. Here add a neighbor. Here to also add a neighbor, right? Then in this case here now you put 0 here. So the same thing here. Here is a neighbor. Here we have a neighbor. Let me make it clear. Here we have a neighbor. Here we just be, here we also have a neighbor. Then here will just be 0. This is simply the 4 by 4 circular Hückel's determinant. This is how easy it is. You don't understood now? Very, very simple. This is how to build the 4 by 4. Right? But another thing is that you should know that for a 4 carbon, right, it is the whole determinant. Each of the terms have what we call beta raised to the power 4. Don't be confused. Why is it like that? Because the carbon atom here is 4 in the simplest format. Now, if you want to reconstruct this again, what do? You divide the whole determinant by beta raised to the power 4. So what do? It's like you simply saying all of them here divided by beta. So here, just like here is beta, here is beta, here is beta, here is beta. So what do we do next? It's simple. So we can now have a new variable that is like this. The new variable which is now equal to x over beta. So if we are to rewrite this one now, right, I will have to erase the board to do it somewhere up here. Please follow me. Follow me so we build it together. Now we come here. So here can simply be, okay, we can replace all this one here with this new term, right? Here becomes 1 because beta divided by beta is 1. Here become 0. Here become 0. Here become 1. Here become this. Here become 1. Here become 0. Here become 0, 0. Here become 1. Here become 0. Here become the new term. Here become 1. Here become 1. Here become the new term. It is from here you can then calculate for the determinant. Is that understood now? So this is how to build this table for a 4 by 4 matrix, in which you can as well come here to say the new variable is equal to, anywhere I see x, now you know it is alpha minus what now? E divided by what now? Beta. So if I'm looking for beta, so if I'm looking for the energy now, I can make the energy the subject of the formula by simply cross multiplying. It become b, okay, alpha minus E. So if I'm looking for this energy here, now energy is not equal to alpha minus. So this is how to look for the energy, and this is how simple it is. So do well to like, share, and subscribe, and make sure you go through it again. This is for 4 by 4. Thank you, and God bless you.